Alright guys, this is the central limit theorem. I wanted to show you guys a visual of the central limit theorem because I think just trying to explain it and draw a picture of it, a few pictures on the whiteboard, just kind of doesn't cut it. So I think this visual maybe will help explain it a little bit better. So basically what the central limit theorem says is no matter what distribution you start off with, and this up above represents our population. This is our population distribution. So it's a very right skewed distribution. We have this much longer area in the right tail than we do in the left tail. And what the central limit theorem says is if you take samples from this distribution, so we're going to randomly sample values from this distribution, and we find the averages of those samples, and we plot those averages down here in a histogram. Right. So if 20 occurs as my average of my sample, I'm going to increase the number of times 20 occurred with a histogram bar down here, and we're going to repeatedly sample over and over and over. This is recording the number of samples that we've taken. We're repeatedly going to sample over and over, and we're going to see how many times a certain average of the samples. So how many times those occurred. That's what we're keeping track of down here. Notice they're on the exact same axis. Okay, 60, 60. Okay. Now I'm going to start it just so you can kind of see what's going on. I'm going to let it run a couple times. So we've almost done 100 samples, and we're making this histogram down here. All right. So in these 97 samples that we've taken of size 1, something down here around 1 has occurred twice. All right, and then maybe 3 has occurred 3 times. All right, this has occurred 3 times. This has occurred 8 times already. All right, this has occurred 6 times, so on and so on and so on. These different numbers. All right, 19 or 20 here has occurred 1 time. All right, so these heights of these bars are recording how many times an average, a sample average, has occurred. So we've taken samples of size 1. So when we're talking about an average, we're really just talking about the number that we picked from this distribution. Okay, so I randomly pick a number between 0 and 60, probably 80, as this goes all the way up to here. And these are the numbers that are occurring. Okay, when I pick those. Alright, so I'm going to let it go for a little bit longer, and what we're going to see is as this number of samples gets bigger and bigger and bigger and bigger and bigger, the distribution of the averages of these samples of size 1 are taking on the exact same shape of the distribution itself. Right? This is basically the likelihood we're going to pick these numbers. Right? If we're thinking about it probability wise, the more likely things that we pick are right in this area where this peak occurs. So that's why these values are showing up the most down here in our averages, because they're the most likely to get picked. Alright, and since we're just taking samples of size 1, this thing is basically perfectly mimicking the shape of this distribution. Alright, law of large numbers is what's taking place here. As this number gets larger and larger and larger, the distribution of the sample means down here on this axis is taking on the distribution of that population. Alright, now like we said before, the average of all these sample means, if I've taken all these 3,120 numbers that we picked from this data set, the average of all those numbers is 14.48. So that literally means that the mean of this original distribution, this population up here that we're sampling from, really is around 14.5. Right? That's what we talked about in class. The average of the sample means is the population mean. Okay, but this distribution is not at all bell-shaped. It's still right skewed, just like the original population was. Okay, now central limit theorem. It says if we increase this sample size, the higher we increase it, the more normally distributed this becomes. So I'm going to just increase it to 4, and we'll see it already starts becoming more and more and more normally distributed, meaning this right skewness is slowly going to make its way out of this, and it's going to become more bell-shaped. Now if we look at it right now, it does still have a slight right skewness to it. Okay, still has a little bit more in the right tail going on than the left tail. Right, but watch what happens again. The magic number here in the central limit theorem is 30. So now we're increasing our sample size to 30. And now when we start this, we get a nice tight bell curve. Right? It's these values in the right tail are not taking place anymore frequently than the values in the left tail, because we're getting a big enough sample. Everything's being pulled back into the mean. Alright, remember the other big part of the distribution of sample mean says that when our sample size gets bigger, the standard deviation of the sample means gets smaller and smaller, and that's why we're getting a really tight distribution around this center, around this 14.3, whatever this is here. Right? Now this is suggesting that the mean of the original population is around 14.33. Okay, and again, this is not a big sample size at all. I mean, 30 is not a big sample size at all relative to most populations, and we have a really nice tight bell shape. And the peak of this bell shape, if you draw these on the same axis like we have here, the peak of this bell curve down below is basically pointing to what your mean is. So up here we can't really see what the mean is. All right, if we remember our properties of right skewed data, here's the mode, that's the peak. So because it's right skewed, the mean is a little bit to the right of the mode, but we still don't have a great idea where it is. But the central limit theorem basically shows us that the bigger that this sample size gets, the tighter this distribution of the sample mean gets, and the center of this bell-shaped distribution of the sample means will point right to that population mean. Remember, the mean of the sample means is the population mean. Alright, and that's the idea of the central limit theorem. Make this thing go all the way up to 50, and it gets really tight around that mean of 14.5 or 14.33.